Let's get started. So I'm going to talk to you about coroutines. This is me. You can find me in various places on the web. I am one of the co-organizers of the Munich C++ user group, which is one of the biggest user groups in the world. Since the pandemic, we have been meeting virtual, which means also for people who are not in Munich, feel free to attend one of our events. If you want to give a talk, practice a talk, give a lightning talk, please reach out to us. We're always happy to welcome new faces. In my day job, I'm currently working as a runtime engineer for Woven Planet, which is the software spin-off from Toyota. And the topic today is going to be coroutines. And if you looked at coroutines already in the shape that they were shipped in C++20, you will probably have noticed that they're quite hard. So on the one hand, they allow for extremely complex transformations of control flow, which makes them very powerful. But they do so through an arcane syntax that changes some of the fundamental rules of the language, which gives the coroutine code a very weird feeling. They're quite hard to understand, but what makes matters worse is that if you don't use them on a day-to-day basis, then it's also quite difficult to remember how they work if you come back to them after a long time. So it's very hard to learn them in a way that they stick, right? And one of the goals of this talk is to help with that problem a little bit. So in particular, I want to provide certain guides and cues that help you to remember them more easily. So if mnemonics, if you want to think of them that way. The feature is too big and too complex to introduce all of it in one talk. So this talk is only focusing on the syntax side. So what is the core language mechanism that is provided in C++20 that you would want to use when you want to implement your own coroutines. This is very different from the user side. If you just want to use coroutines as they are provided by a library, then you actually don't need to care about most of this. So this is really about the guts of the language features, which also means we have to look at all the really complicated parts. But don't get scared away by this if it's too much to take in. If you just want the user's perspective, then most of this actually doesn't matter. But we're here to look at all the technical details. So what are we going to do today? We're going to have a very quick look at the essential use cases for coroutines, why we want them in the standard. Then we're going to examine them from a caller's perspective, how a user of a library would interact with them, for example. We're going to look at all the steps that are necessary to start up a new coroutine. We're going to then look at suspend and resume, which is the core feature of coroutines. And then we're going to try to draw a map of coroutine land that will help us to navigate all of the complexities of the features and thereby get an idea for how we can interact with coroutines in our code. So a short disclaimer up front. As I mentioned, the feature itself is extremely powerful and flexible. And it's very hard to squeeze all of that into a one-hour talk. So I'm going to simplify things in places. I'm going to ignore some of the more advanced features just to keep explanations streamlined. And all of the code that you're going to see is slide code. It's going to be very reduced, so please don't take this as best practices for writing coroutines code. It's just meant to illustrate certain points, but it's mostly not something that you would write in real-world code. So with that, let's take a look at the basics. So the barest essentials are that coroutines is something that you can think of like a function that can be paused in the middle, right? So you're executing up to a certain point, and then you said, now I press the pause button. The function stops executing, control flow returns to the caller of the function, and now other stuff happens, and at some point later then you can resume execution of the coroutine, and the function will just continue executing right at the point where you suspended it earlier. And all of the surrounding state will still be intact. So that's the core features, right? Like all of the local variables that you had on the stack for the function, when you resume, they will be exactly in the state where you left them. A consequence of this is that the coroutines always have to be stateful necessarily, right? Because all of this local state needs to be saved somewhere when you go into suspension. So if you think of like when you call a coroutine for the first time, don't think of it like a function call, but think of it like a factory function that creates this state, right? And then like the actual execution is something that might be triggered in various ways afterwards. But really like when you see a coroutine call, really think of that like a factory function. And we will see an example for that very soon. Lastly, the coroutines that we have in C++ 20 are stackless coroutines. That means whenever I suspend a coroutine, controlflow always returns to the immediate caller. A consequence of that is that I cannot suspend from something that is not itself a coroutine, and I cannot suspend through a normal function, right? Like if you think, for example, you're calling an algorithm, and then you pass a predicate to the algorithm, and you want to suspend like from the predicate through the algorithm back to the caller, that won't work because the algorithm itself is not a coroutine. Coroutines in other languages don't have this limitation, but in C++ we have this. So let's look at some example code. So one of the most important use cases for coroutines is asynchronous computation. And the example for that is like, if you used ASIO, you've probably seen stuff like this. So you want to read some data from a socket. This is an I/O operation that might take a long time to complete, right? The easiest way to do this is just to call the blocking read function, right? That will just block for some time, and eventually you get the results back, like an error code, and the number of bytes read, which were filled into the buffer. So since this is a blocking call, it's not very nice. It doesn't scale very well. So you usually want to use an asynchronous API for this in like real-world applications. However, the asynchronous call looks very different from the blocking call, right? Now, instead of getting the return values back, I have to pass a callback as an argument to the function. And what now happens is that when the read completes, this callback gets invoked, and what was before the return values, the error code and the number of bytes read, is now passed as arguments to this callback. And if you ever worked with an API like this, you will notice that like this creates a weird inversion of control flow that makes it quite difficult to interact with this API, especially if you're not used to working with that. If you write a lot of code like this, eventually you get used to it, but there's a barrier of entry and there's an additional complexity. In particular, if you think like this read call happens inside a complex function that is doing lots of other things before and after. The problem is when you actually wake up inside the callback, all of this surrounding context from the function that you had before is gone, right? So you need to manually transfer all of that into the callback to be able to do whatever you want to do when the read completes. And that's where the complexity comes from. So what coroutines allow you to do is they transform the second call so that it basically looks like the blocking case. So you now do an async read and you call co-await on this. And the control flow will be the same as before, right? So with the async read, you will stop executing the function at that point, and you will be woken up like the same as with the callback when the read completes. But because it's a coroutine, now all of the surrounding state is still intact. So the code looks pretty much exactly the same as it did in the blocking case, which is much easier to reason about. Then there's a second use case, which you see often, and that is suspended execution. So think of like some computation. You want to start the computation, and then at some point you want to say, okay, I'm going to stop, and you need to provide me more data before I continue execution, right? And so the user like continually provides data, and the function always like executes some small step. It might return some partial results, but like it moves forward in like individual steps. The simplest case of this is a generator function, which like simply like generates values whenever you call it that you can then iterate over. And we will see an example for that right now. Because like the first example that we're going to look at is, think you want to write a generator that just generates a sequence of numbers, right? Let's say I chose here as an example the Fibonacci numbers. I just want a function that generates me this sequence, right? So if you're presented with this problem, the first thing that you might come up with is probably an interface like this. So I just specify as an argument how many numbers I want to generate, and I give you back a vector with all of the numbers of the series. So if you think about this for a minute, you can probably see some disadvantages of this interface. So one thing that you might notice is this actually requires you to allocate all of the storage for the series upfront, right? So if you generate n numbers, you need like n storage for n integers. And in some cases that's okay, but in many cases when you process a range like this, you process them element by element. And you don't need to save all of the range at once, right? It's enough if you like get the individual numbers to process it. So yeah, having to allocate all that storage up front is potentially wasteful. Another limitation is that this only works if you know your n up front, right? You can't just say, okay, like, let's just keep generating, pretend this is an infinite range, and then at some point I'm going to stop generating more, but I don't know when, right? This is quite difficult to do with an interface like this. So how could we address these problems? What would be a better design? So one thing that you could do is you just say, okay, instead of like returning the range saved in a vector, I'm going to give you a generator object which is able to give you all these numbers. So I'm going to give you back an object. This object has a next member function. And whenever you call next, you get the next number in the sequence as a return value from this object, right? And this is something that you can write, right? Like if I gave you an interface like this and said, like, please implement this in C++ 11 or even 98, you could do this, right? So is make Fibo generator, is that actually a coroutine? And it doesn't have to be, right? The answer to that is maybe. It could be a coroutine, but it doesn't have to. And that's an important thing to realize. Like coroutines don't allow you to implement something that you couldn't implement before. They just make it easier, right? So it doesn't increase like the expressive power of the language. It just makes it easier to express some things and also makes it more efficient in some cases. So the only thing that we see here at this point, like from the user's perspective, is the interface of the coroutine, right? And we don't actually know whether it is implemented in terms of a coroutine or in terms of normal function code. So if we just look at the signature, the most important thing that we get back is this return object from the function. And its type, its interface determines how we interact with the underlying coroutine. So that is the first the first thing that we're going to look at now. So I said in the beginning, think of a coroutine call like a factory function. And the return type, that is what your factory function produces. And like conceptually, what this contains is the state of your coroutine, right? So we said the coroutines are always stateful. They like contain whatever state the function has when it's suspended. And the factory function is what creates that state. And the interface of this return type determines how you can interact with the coroutine, right? Like how you can resume it, what data it gives you back. And you don't need to understand anything about the implementation. If you understand the interface of the return type, that's enough that for you as a user of this function to know. And you don't need to know anything about coroutines. And there's actually no way to tell from the outside whether it really is a coroutine. And the important thing is the return type is just a class type like any other, right? And we can do whatever we can do in normal classes. We decide what the interface is as the implementers of the coroutine. So if we cannot tell from the signature whether a function is a coroutine, then what actually does determine whether it's a coroutine or not? So the answer to that is quite simple. It's a coroutine if the body of the function contains one of these three keywords. That's the rule, right? If the compiler sees one of these three keywords in the body, it says, okay, now it's a coroutine, and all of the coroutine rules apply. And that actually has quite drastic impact on the rules for what can happen in this function. Just as a simple example, you cannot use the return keyword inside the body of a coroutine. That will not compile. You have to use the co-return everywhere. So let's look at a very simple example. Let's say I want to implement my Fibonacci function as a coroutine. And this is what that would look like. So we have the co-yield keyword in there, which makes it a coroutine. But otherwise, like this looks actually like if you like mentally think of like the very first version that we had that just filled the vector, it would actually look pretty much like this, right? The only difference is that instead of the co-yield, we would do a pushback into our result vector, but the overall control flow is exactly the same. And that's very much by design, right? Because like the filling of the vector, that's the most simple, most straightforward way to generate this series. And the coroutines allow us to use that simple control flow. So we still don't really understand how this works, right? Like the co-yield is there, but everything else makes no real sense. Like, for example, this Fibo generator return value here, where's that generated, right? You don't see a Fibo generator anywhere inside the body. So for the rest of this talk, we will actually try to understand what's going on here, what's going on under the hood, and how we can write a function like this ourselves. So let's take a step back, and let's try to write the simplest, smallest coroutine that we can think of. So this is the simplest one that I could think of. It's basically empty. I need to put like one of the three keywords in there so that it's not a function but a coroutine, so I just use an empty co-return, right? That's all I do. So this doesn't compile because I didn't define my return type yet. So that's the next step. So again, let's try to do the simplest possible thing. Let's try just an empty type, right? And now the compiler is going to complain. It's going to complain that it cannot find the nested promise type for this return type. Okay, let's try to make the compiler happy. Just put it as a nested struct in there. And this now actually gives us the second important player in the coroutine mechanism, and that's this promise type. So what is this promise type? Why do we need this? So if you hear the name promise type, you might think of future promise from the thread library. And the coroutine promises work somewhat similar. it's different, but like as a very rough analogy, in future promises, the future is the thing that you give back to the caller. The promise is the thing that you keep inside the thread, where you actually like put the values, like it's the future is the one side of the communication, right, that you give back to the caller. The promise is the other side that you retain inside the thread. And it's kind of similar here, right? You have the return object that you give to the caller of the coroutine, and the promise type is the thing that remains like within the coroutine, so the other end of the communication channel. But don't take this analogy too literally, right? Because apart from this, the coroutine promise looks completely different. So in particular, one of the responsibilities of the promise type in coroutines is that it determines what happens at essential points in the coroutine lifetime. So it allows you to customize what happens on start and completion of the execution of a coroutine. And it also allows you to customize what happens when you exit the coroutine through a co-return or through an exception. So let's try to implement a simple promise type. If we try to compile the code as before with an empty promise type, we again will get a bunch of compiler errors that it's missing a bunch of functions inside the promise type. In particular, the first thing that it wants is a function called getReturnObject. And this now resolves the mystery where the actual return object that our factory function returns to the caller comes from. Because what will happen is the compiler will magically, behind the scenes, call this getReturnObject function on the coroutine, store the object generated here in a special place, and then when the coroutine suspends for the first time and control flow is returned to the caller, it will hand out the object that was created here to the caller, right? So that's why we didn't see the construction of the return object in our makeFiboGenerator function before, because it actually happens here inside the promise. The second thing that we need to provide is a handle for how to treat the return value. In this case, I just had an empty co-return statement, so I need to provide the return void function. If I actually return a value in my co-return, then I need to provide the return_value function here. In this case, I'm just not going to do anything with the return value, so I leave this empty. I also need to give an implementation for unhandled exception. Like if I exit the coroutine via an exception, then this is the customization point that's being called. Again, I'm not going to do anything here. And then I'm going to provide two functions, which are kind of curious, initial suspend and final suspend. And they allow me to customize what happens. So with the initial suspend, that is like right after the coroutine was constructed. Do I want to suspend, or like what should happen on this initial suspend? And for the final suspend, like what should I do if I reach a co-return and the coroutine flows off the end of the function? So it's like I reached the end of the coroutine, right? These are the two points here. And like the other three functions, that's pretty straightforward what they do, but like these two are now, again, a bit mysterious. They have like these weird special return values, suspend always or suspend never is what you typically find there. But we don't really understand how that works, so yeah, those are a bit mysterious for now. But if we get to this point, then our code actually compiles, and we can play around with it. And what we see is if we have the initial suspend, return suspend always, then what happens is when I call my coroutine, so I now added a print statement to like make the control flow visible. And if I now call this, then I don't actually see anything printed to the console, right? So the coroutine starts, but it's suspended immediately. So I never actually reach the print statement. It never executes. But if I change the return value from the initial suspend, from suspend always to suspend never, then I actually do see the print statement, right? So then the coroutine it doesn't suspend, it doesn't pause at the beginning, but it continues execution into the body of the function. So this is already something that we see now, is that like through the return value of this initial suspend function, we can push the pause button, right? We can suspend the execution of the coroutine. So let's try to understand what is actually happening there, what's going on there. And for that, we have to introduce like the last major component of the mechanism, and that's the awaitable. So what's an awaitable? The simplest way to think about it, and the way that I like to think about it, is the awaitable is something that you can call co-wait on. Okay? If you think like co-wait is like an operator, and the argument of that operator has to be an awaitable type. Okay? So like anything that you can call co-wait on, that's an awaitable. And we will see shortly what the requirements are that make a type a valid awaitable. Conceptually, every call to co-await is an opportunity for suspension. That means whenever I call co-await, the awaitable decides whether the coroutine is suspended or not. So it can also, like if the awaitable decides so, then the coroutine can just continue executing, doesn't go into suspension. But it's an opportunity for suspension, right? So if I want, then that's where I press the pause button and return control flow to my caller. The awaitable allows us to inject code that is executed before we suspend and after we resume. Similar to how the promise type allowed us to customize what happens when the coroutine starts or returns, the awaitable allows us to inject code for suspend and resume. So let's try to do the same thing as before. Let's try to implement the simplest possible awaitable. If we start with an empty type, it will complain that it's missing 3 functions. The first one that I need to implement is await ready. So await ready is called by the compiler to determine whether I actually want to suspend at this point. So if await ready says, no, I'm ready, so it returns true, then that means we don't go into suspension, right? We're ready to continue execution right away, and then we just go on. Like if you think, for example, if you do asynchronous I/O, right? You might already have the data in the local buffer, so you don't need to go to sleep, right? You can just continue execution. So in that case, await ready would just return true, and you don't suspend. If it returns false, then we actually trigger the suspension mechanism, and then the next thing that's getting called is await suspend. Await suspend gets passed as an argument this coroutine handle that we didn't see before. And this is basically, this is the code that gets executed right before we go to sleep, right before the coroutine goes into suspension. So this is where we need to set up all of the stuff that we still need to take care of before we are being paused. The coroutine handle, the easiest way to think about it is, so we set the coroutine function is like a factory function that generates this coroutine state somewhere. This coroutine state is created by the compiler automatically in some magical place, right? Like the promise type, for example, that's not something that we as the user create. The compiler creates that for us behind the scenes and stores that away. Similar to like all the state inside the coroutine body that all gets created implicitly. The coroutine handle is like a pointer to that state, right? That's how you can think about it. And the important point is it's not a smart pointer, right? There's no RAII semantics here. It's just a pointer. That's the simplest mental model for this. And we will look at what you can do with it in a moment. Then the last function that is missing on the awaitable is, one more thing. The coroutine handle, we had it here with the empty template brackets. You can also have that specialized on the promise type that we saw. And this is the promise type that we had earlier also. And then like the counterpart to the await suspend is the await resume. That gets executed like, so our coroutine is in a pause state. The caller now does other stuff in the meantime. And eventually we want to resume execution of the coroutine. And immediately before the coroutine wakes up and continues where it left off before, it calls await resume. And we can like bring it back to a state where it can continue execution. So those are the three functions on the awaitable. And the easiest way to implement this is to just say, like, on the await ready, I'm just going to return false. So I'm never ready. I always want to suspend. And I just leave the other two empty. And if I do it like this, then this is actually the suspend always that we saw before. So std suspend always, that's the implementation for it. And you can probably guess what suspend never will look like. It's exactly the same, except the return value is true there, right? We're always ready. We're never going to suspend. So now the only thing that we need to look at, we're almost through it. I know this is a lot of stuff, but we've seen almost all of the stuff. I just want to quickly take a look inside the coroutine handle, what is in there. So the coroutine handle has an interface. In particular, it provides a resume member function, and that is the thing that I need to call if I want to wake up the coroutine again, right? I can suspend it by calling callweight inside the coroutine. That's what puts it to sleep. But then if the caller wants to wake it up again, it needs to call resume on the coroutine handle. The other important function that we have here is the destroy member function. And that allows us to destroy the coroutine. So in particular, if the coroutine is suspended at any point, I can always call the destroy function on the coroutine handle to like safely shut it down. And this cleanly shuts it down, right? It frees all the resources, calls all the destructors. So this does what you would expect. But you have to call it manually, right? It's not a smart pointer, it's a raw pointer. So you have to decide where you call destroy. Or whether you call it at all, right? Because if the coroutine just runs to completion, control flow just flows off the end, and you don't suspend on the final suspend, then it cleans up itself. In 90% of the cases, you don't want to do this, but it's a possibility. And then the other two functions that we have here are just conversion functions that allow us to convert the coroutine handle to the promise type, or a static function to construct a coroutine handle from a promise. And those last two only work if we use the version of the coroutine handle that is specialized on the promise type. Right? So in some cases, it's just enough to know, like, I have some coroutine handle and I just want to resume or destroy it. Then you can just store the unspecialized coroutine handle, right? Especially if you have like a generic list of like many coroutine handles. But if you want to interact with it in some more involved way, then you usually have to call these promise conversion functions at one point, and then you actually need to know the promise type. So that was a lot of stuff. So let's start by writing a little cheat sheet of what we have so far. And the way that we read this is, if we read this from top to bottom, then it actually takes us through all the different steps that the compiler goes through in the execution of a coroutine. And whenever we see a slash on a line, that means like we have the option to either take the one or the other. So like in the beginning, as we've seen, we need to specify the return type for our like factory function, coroutine function, and that that can either be like directly the struct of the return type, as we saw in the example, or you can also specify this through a coroutine traits function. And that is useful if, in particular, if you deal with return values, with return types that were not designed with coroutines, right? Like you can have a coroutine that just returns an int, or even returns void, and you can make that work if you like customize it through the coroutine traits. But mostly you want to use the return type. Then the return type, through its nested type def, points out the promise type. The promise type gets constructed implicitly by the compiler on the first call to the coroutine. And one neat feature here is if we provide a constructor on the promise type with a signature that matches the signature of the coroutine function, then we get past the arguments that were passed to the initial call of the coroutine also here to the promise constructor. But this is purely optional. Then the next step is that the promise getReturnObject function gets called to create the return object. And then the initial suspend function is called to determine whether like the coroutine should suspend right away or whether it should continue execution. And that's the entire startup. And then when the coroutine actually finishes execution, we go through the shutdown steps. So first, depending on what kind of co-return we have, we either need to have a return value function that gets passed the return value that was given to co-return as an argument, or we have the return void function. We need to give the unhandled exception in case that we exit the coroutine through an exception. And then lastly, the final suspend is called just before the coroutine ends execution. And then we also have the awaitable with the three functions: await ready, await suspend, await resume. And hopefully, like now, just from seeing the names, you can still remember what those do. And those are all of the key components. This is a lot to take in, so if you're feeling overwhelmed, that's completely normal. But you're now through the worst, right? Now you've seen everything once, and the only thing that we now need to figure out is how they connect. What is the interaction between the two? But if you understand like the roles of the individual things, right? So the return type, that is what is given back to the caller. That's the interface to the coroutine that determines what we can do with it. The promise type, that is like the thing that remains within the coroutine, and that customizes all of the actions on start and shutdown. And the awaitable is the thing that you pass to the callweight call. So this determines what happens when you try to suspend a coroutine, right? So these key roles you should keep in mind. And then, yeah, the coroutine handle is just a pointer to the state. And now we can actually talk about resuming coroutines, right? So we saw before with the simple example where we had the initial suspend, how we can put a coroutine to sleep, but now we want to wake it up again. So let's go back to our example from before, right? I have my hello from coroutine. If I just call the hello coroutine, it goes into suspension right away. I don't see the print on the console. Now what I want to do is I want to resume it again. So I need to provide on the interface of the return type some way to resume it again. And we already saw that the only way to resume a coroutine is to actually call the resume function on the coroutine handle. So what we need to figure out now really is how can we get from the return type to the coroutine handle? Because like what we have so far is like we have all of these things, but they're all disconnected, right? So the caller has access to the return type, right? Because that's what we hand out. That's what he gets back from the factory function. Similarly, the coroutine has access to the awaitable, because like the coroutine calls the callweight, and the awaitable, that's the object that we handed there. And we can get from the promise to the coroutine handle and vice versa via these conversion functions. But other than that, this is all a disconnected mess. So let's try to make some acquaintances now. So the first thing that we see is, if we remember on the promise type, we had this getReturnObject function, right, that creates the return object that we hand back. And you can see already on the colors, here we have like two components that are disconnected so far, and we have them both in the same place. So what we can do is, like getReturnObject, that's just a function, right? We can do everything in there that we do in a normal function. And I'm just going to say, okay, when I construct my return type, I will just pass it the coroutine handle as a parameter to the constructor. And then inside the return type, at the bottom, I have the constructor that gets the coroutine handle as an argument, and I just store it inside a member variable, right? This is just, there's nothing magical here. This is just like how normal classes work, right? And now, since I have the coroutine handle in a member variable, implementing the resume function that the caller has to call to wake up the coroutine is really easy, because it will just call the resume function on the handle. And again, in 99% of the cases, this is how you want to do this. So in particular, if you're suspending on the initial suspend, you need to store away the coroutine handle somewhere. So you either give it to some external entity, like a coroutine manager, thread pooly thing, scheduler, whatever, or you give it back to the return type. If you do either of these things, you just created a coroutine that you can never access again, right? Because it goes into suspension and then it's over, right? You need to get the coroutine handle to a place before that. And this is the typical pattern. This is how you usually want to do it. You just give it to the return type, and then the user has access to it through the return object whenever it wants. So that gives us our first connection here, right? So the caller can use the handle that is stored in the return type to get to the coroutine handle of the promise. What is still missing now is the coroutine and the awaitable. They're still disconnected. So what can we do there? And the connection point here is the await suspend function, because if we remember back, that gets past the coroutine handle to the function that we're about to suspend as an argument. So again, also here, through the await suspend function, we can get to the coroutine handle and to the promise. And now we have all of the parts connected, right? So the getReturnObject, that's the initial connection between the promise and the return type. And then through the handle member and the await suspend function, it's all connected. And now let's actually try to implement some simple coroutine logic using this. There's really two essential things that you need to be able to do. And if you understand how those works, then you basically have all the basics in place to do coroutines. And this is, how do you pass data from a coroutine to the caller, to the function that you suspend to, and the other way around. How do you pass data from the outside into a coroutine when you resume? If you can do those two things, then all of the other stuff you can basically do yourself. So let's look at those essential examples. So first, the direction, how can I pass data from the coroutine back to the caller? So start in the coroutine, right? And I'm calling callweight. So I somehow need to pass the data to the awaitable. How do I do this? So in this case, the coroutine, it just does a callweight, and the value that I want to return is here the integer 42. The only thing that I can do at this point is pass it to the constructor of the awaitable, right? That's the only thing that I can do at this point. So let's do this, right? We pass 42 to the constructor, and we just store it inside the member variable of the awaitable. So now the data is in the green awaitable. But the caller cannot get to the awaitable, right? So I need to store it further down inside the promise. And the way that I do that is on the await suspend function. That's when the awaitable gets access to the promise. So here I use the coroutine handle to get to the promise and then store the value inside a member variable of the promise object. So now I pass the data all the way down here to the promise. Now I need to get it back to the caller. So the path from the caller is it has to go through the return type to the handle, and that's how it can reach the promise. So this is how the bottom is how the code would look like for the caller, right? I call the coroutine, and when it suspends, then I know the value has been stored, and I use the getanswer member function on the return type to get it back. And the implementation for getanswer is just I go from the handle to the promise, and the promise has the value as a member function. That's where we stored it before. And that's the complete path. And like with this picture, I hope that this is something that you can work out, right? That helps you remember what the control flow looks like here. So let's now take a look at the other way. I want to get data into a coroutine from the outside. So here I have to start on the caller side. Again, like the common point of interaction is the promise. That's always where we need to get to. So for the caller, it would look something like this. So I have a coroutine. At some point, the coroutine suspends. It cannot continue execution until I provide it with more data. So in this case, I provide it with more data, again, the number 42 as an example. And now, when I call provide, it stores this value, it resumes the coroutine. And when the coroutine continues execution, so at the top you see the callweight call, that's where we go to sleep, right? That's the point where the coroutine said, I need more data, I want to go into suspension here. And now when provide resumes the execution, then the callweight wakes up, and the return value of the callweight operator, that is now going to be the 42, right? So when I resume execution, then the answer variable inside the coroutine will contain this value 42 that the caller passed in. So how can we do this? We saw in the diagram that we need to go through the handle on the return object to the promise. So that's pretty straightforward, right? So this is the implementation of the provide function. Again, I just call like the promise function on the handle, go to the member variable that I created inside the promise and just store the value there. And then I call resume so that the coroutine actually wakes up and can do something with this value. I don't have to do this here. I could also like decouple it, have one function that just stores the value and have another that resumes it. But like this is the typical pattern that you find that it happens in the same function. So again, now the value lives in the promise. So how can we get to it from the other side? So the coroutine, again, has to go through the awaitable. So the only place where how the awaitable can get to the promise is on the await suspend, right? But the await suspend is only part of the picture, right? Because when we call await suspend, that is before the caller provided the data, right? That's when the coroutine goes to sleep. So I cannot actually do anything at this point except store the handle that I get passed as an argument away somewhere, right? and now the caller needs to do its thing, needs to provide me with the data, and only when await resume gets called, then I can actually retrieve the value from the promise. And what happens here, the part that we did not talk about, is that now the return value of the await resume is also going to be the return value that falls out of the co-await call that the coroutine did earlier. So this is one missing arrow here, right? The return value of the await resume, that is how we hand the data back to the coroutine. So let's go back to our example from the beginning again. So here we had like the Fibonacci generator, and we wanted, so we can now just say we do the co-await, and we have this awaitable, new number awaitable, and that's how we hand the data in, and then we do the whole dance that we saw before, like for getting the data out of the coroutine. And we can do all that, but this is a lot of boilerplate that we have to write for a very common pattern. And that's why we get a shortcut in the language for this. And if you remember back to the example, what we actually used there was this co-yield keyword. And co-yield is really just syntactic sugar, right? Like if you understand co-await, you can already do everything. With co-yield, it's just a little bit easier. In particular, the only thing that co-yield really does is, so if you think of this code, right? What you need to do here is you need to specify the awaitable, right? You need to say, this is the awaitable that actually handles the whole mechanism. And with co-yield, you just say, this is the value that I want to give out. And the only thing that co-yield does is, the compiler goes to the promise type, and it looks for a yield value function. And that yield value function now tells you what the awaitable is that is going to handle the mechanism. So it's like you can always transform this back to this in your head very, very simply by looking at what the yield value function does. So it's really just a shortcut for a co-await call. But it's a significant shortcut because you might notice the yield value function now is on the promise type, right? Before, we always had the thing we called co-await on the awaitable type. But now we're calling yield value on the promise type. So that gives us a shortcut, right? I can just now store the value right away in my member variable, because I'm already in a member function for the promise. And I don't need a complicated awaitable at all, right? I just say suspend always, and it works. So that's the true power of co-yield, that it gives me a shortcut from the coroutine right to the promise. And I don't have to, in most cases, I don't even have to write a custom awaitable to make this work. There's one last thing that I want to talk about, and that's a really cool feature called symmetric transfer. Normally with coroutines, when we go into suspension, it's always, we give control back to the caller, right? So in the case of the initial call, whoever called the factory function, did the initial call to the coroutine, that's who I return the control back to. In case of suspension, whoever called resume, that's the one who I hand control back to. In some cases, what I want to do, though, is not hand the control back to the caller, but hand the control to another coroutine. So in particular, if you think about use cases like cooperative multitasking, right? Then I have a bunch of tasks, they're all executing, and they just want to hand control flow to each other. And this is something that you can do with symmetric transfer. And the way that this works is, on the await suspend function, So before the await suspend function, always return void in our examples. If instead of returning void, I return a coroutine handle, then that means I want to do a symmetric transfer to that coroutine, right? So the coroutine handle points to a suspended coroutine, and now the await suspend function will actually, like, it will swap out the coroutine frames, right? Like the currently running coroutine will go to sleep. It will like free up the stack, and then the new coroutine will start executing in its place. And what makes this a bit confusing is that we now have two coroutine handles on the same interface. So the one that we have as a function argument, the one on the bottom, that is the coroutine that is going to sleep. That is the coroutine that's about to be suspended. And the one that is being returned, that's the coroutine that I want to transfer control to. So one possible implementation that I could do is say, like, if the promise has a handle to another coroutine, then I will just wake up that one. If it doesn't, then I will just return myself back so I can do more work, right? If somebody else wants to do work, I hand control off to them. If there's nobody else, I just continue execution. So that's a simple example for this. All right. So this was the whole mechanism. This is all the syntax that you need. If you understood all the examples, and you probably haven't understood them all from the talk, but I hope that this gives you enough material to now start sitting down and start playing around with them. These are all the basic principles. You can construct everything else pretty much from just this. Learning the syntax is the boring part here. Right, this is not exciting, but this is also the easy part. Understanding how to now use them efficiently and effectively, that is much more difficult, but it's also more fun. So I hope now if you visit an advanced coroutine talk at another conference maybe, then this will help you to like understand this better and actually enjoy the fun parts about it. Designing libraries around asynchronous control flow is a very deep topic, and I hope that we will see many talks in the future that actually focus on this and don't have to get stuck up on all the technicalities that we talked about today. For now, I just hope that like this cheat sheet that we created will help you like navigate this part of the language a little bit easier in the future. So again, like, for the return type and the promise type, just read it from top to bottom, and hopefully like you can remember what is actually happening there in the different phases. For the waitable, like I think the three member functions are mostly self-explainable. And then this, which I think is the real money maker, that allows you to understand how it's all connected and how you can pass data between the different components. Some references for you. And if you want to have like all of these diagrams on a single A4 page, this is a QR code to a PDF that contains this. Yeah, with that, we have a little time left for questions, and thank you very much. Hannah, please.
Okay, yeah. I have a question. Is there a way how to provide allocator to coroutine? So it will be constructed on the allocator?
Right. So the thing with the allocators is like I mentioned this briefly, that the compiler has to create all of the promise type and all of the state in like some magical place. And usually that means it has to do a heap allocation, right? And if you're in an environment where it's not, where you can't just call operator new, you might want to use an allocator for this. The way that you do this currently is that you have to overload operator new. That is the customization point. This can be a bit tricky to get right. So, but in principle, it works. So you can make it work, but it's, yeah, if you've never used allocators before, you're in for a treat. But yeah, I've tried it, and it works in principle. Other questions? Oh yeah, one more. Please.
Thanks for the talk. So many of us have probably used ASIO, and if we go back to one of your first slides, you compare a blocking read and a read with callweight. This is what I want people to use. Right? Just swap out the callback and the callback hell that comes with ASIO with just callweights, basically. But then you've got this 1 hour talk that is very dense, explaining all of the details of coroutines and how they work. How much do you think we can omit the part where we teach people how coroutines work and just teach them, well, effectively swap out your callback, just use callweight. Don't worry too much about the implementation. It's complicated, but don't look too much in the box.
If you already have a library, and ASIO is probably the best example for that at the moment, that provides these primitives, then you don't need to know any of this, right? You can completely ignore this talk. And that's the good message. The bad message is that at the moment we don't have a lot of libraries with this. And in particular, we have no support in the standard library for any of this. Like we're going to get generators now with C++23, but generators are by far the easiest of this. So for now, if you want to play around with this, usually you have to go to this level. But eventually, like if you have a library that does something useful like ASIO and supports coroutines, you don't need to know this at all, right? You just look at the interface of the return objects that you get back, and then you know all that you need to know. With ASIO, it's a little bit more because you want to co-await yourself on the calls, so you need to understand a little bit about what co-await does, but you don't need to write your own promises or your own awaitables. You're spared by that. The ASIO examples are actually pretty awesome. So if you want to play around with this in a real-world context, look at ASIO's documentation. It's really great. Mathieu? Oh, the mic is off. Did we run over time, or? Did we want? No? Did you just want to say it, and I will try to repeat the question?
Yeah, sure. I guess the question, I just wanted to know, can you suspend a coroutine on a thread and resume it on a different thread? Or is there anything that...
So the question is whether you can coroutines across threads, and I guess like in particular whether you can suspend on one thread and resume on another. Yeah, that works perfectly well. I mean, you need to take care of like all the obvious like threading concerns, that like you don't introduce races and you don't do something on the resuming thread that is not safe for some reason. But in principle, yeah, you can just take the return object, pass that off to another thread, and that will work. Yeah, no restrictions there. And then like one last question before we wrap up.
So what is the actual cost of using coroutines?
The what?
The cost.
The cost, that's a good question. So the nice thing about the C++20 coroutines is that they allow very aggressive optimization by the compiler. In particular, if the compiler can like statically verify certain properties of coroutines, it can make them disappear completely. It can even like omit the memory allocation and all of that. But it depends on the use case, what you want to do with them, right? So the more complex like your logic is surrounding coroutines, the more costly they get. But the most expensive part is really the creation of the state, right? The heap allocation that you have to do there. That is actually the expensive part. The suspension and resuming, that is quite easy to do, right? Because all of the objects are already in the correct place, and now you just move around the instruction pointer, right? So it's really not more expensive than a function call in that sense. And that's actually one of the good parts of the C++ coroutines, that they're extremely efficient, especially compared to coroutine implementations in some other languages.
Thanks.
Okay then, and with that, we're on time. So thank you very much, and have a nice day.